Hi, I'm Mr. Kwang. We'll be doing the next topic, work, energy, and power. Alright, so we'll be going through most of the content for this set of notes, but not everything because we are a bit tight for time. We only have one session for this, only 1.5 hours. So I'll just bring you through some of the key content. Okay, so what I'm going to do for work, energy, power, right? Essentially, we're going to study work, which is the link between force and energy, conservation of energy when we talk about no loss between conversions in theory. Okay, then we learn how to use the work energy theorem and conservation of energy to solve mechanics problems. Okay, we also learn about power and efficiency concepts. Some of these things are not new to you, but it's a good chance for you to do some revision if they are not new to you as well. Alright, so let's start proper. Okay, first let's look at the definition of work. Okay, the work done by a force on the body is a product of that force and the displacement of the body in the direction of the force. Okay, so we break this down into a formula. Work done by a force F is equals to F times S multiplied by the angle between them, cosine theta. Okay, if you remember your math, this is essentially a vector dot product. Alright, so you should get a scalar quantity when you do this step. Okay, so the unit for work done is joule. So 1 joule is a work done by a force of 1 Newton when its point of application moves through a displacement of 1 meter in the direction of the force. So basically, if I apply a 1 Newton force on an object and then it moves by 1 meter in the direction of the force, okay, like this. So this is basically 1 joule. When you multiply 1 Newton by 1 meter, you get 1 joule of work done. Alright. Okay, so yep, this is the formula, and of course because the angle between them is 0 degrees, both of them are parallel, so this is equals to 1. Alright, so let's look at a bit more complex example. I have an object of weight 40 newtons placed on a rough surface and the force P equals to 120 newtons is applied at an angle of 60 degrees to the vertical. The friction F acting on the object is 50 newtons. The object moves 5 meters as shown. Determine the work done by all the forces acting on the object. Okay, so this is a setup. You have the same diagram in your notes. So let's look at this a little bit more in detail. Right, so let's mark out this object first. Okay, and I have indicated that the movement is 5 meters in the horizontal direction. Okay, so the first force we have, so first thing we do is calculate work done by each force. Okay, so first force we have the weight. Okay, work done by the weight. Okay, because the weight is at 90 degrees to the displacement, the angle cosine 90, so this is whole thing is equal to 0. Okay, so if you are perpendicular, you have no work done at all. Okay, next force we are looking at is your normal reaction force. This is from the table or from the surface, the rough surface we have, right? So again, you can see that this force is at 90 degree angle to your displacement. So in this case, normal reaction force also has no work done. Okay, next up you have your frictional force, 50 newtons to the left while the displacement is to the right. So if you multiply this, you will multiply by cosine 180 degrees because the angle between the frictional force and the displacement is 180 degrees. So in this case, this is a negative 250 joules. Okay, this negative does not mean that it's in a different direction. It is a scalar quantity. It's just a negative number. Alright. Next, you have your applied force at 120 newtons, but this is at an angle of 60 degrees. Okay, so if I apply this correctly, okay, this angle here, okay, why is it cosine 90 minus 60, right? Because I want the angle over here. You can see where my mouse is. I want this angle between this horizontal line and my applied force. So this will be 90 minus 60 degrees. Okay, I do the step, I'll get 520 joules. Okay, so if you do this, if you sum them up, you get the total work done. So it's just 520 plus negative 250. So I get a total of 270 joules. Alright. Okay, moving on. Okay, let's look at what we have now. Okay, example 2 state we have 3 situations which represent examples of work done by a force on an object, whether it's positive, negative, or 0. A person tries to break down a heavy door by exerting a force against it, but without success despite becoming exhausted. So we look at this becoming exhausted. We know that the person will have sweated and stuff, but is there work being done or not? Remember, he tried to push open the door, okay, but the door did not move. Okay, so in this case, there's no work done on the door by the person, as the door is not displaced nor moved. Okay, next we have a book or an object falling under its own gravitational force onto the ground. G force is pulling the object towards the ground. The object is falling towards the ground. So in this case, this is positive work done by the book by gravitational force. Okay, since the weight is acting downwards and the book also displaces downwards, my force and my displacement are in the same direction. Okay, waiter carries a tray above his shoulder by one arm straight across the room at constant speed. Alright, his arm is exerting an upward force. Alright, so but the tray is moving horizontally. Okay, so there is no work done at all since my force and displacement are perpendicular to each other. Right? So let's look at the summary of what's going on here. If I have if my two forces are parallel, my force and displacement are in the same direction and they are parallel, my theta is 0 and so my cosine theta is 1. Okay, and of course I look at the other extreme end. If it's opposite direction, cos theta equals to 180, cosine theta is minus 1. Okay, then the rest in the middle I think is quite straightforward, but you just need to note that what happens if you have positive or negative work done. When you have positive work done, you are transferring energy into the object. When you have negative work done, you are taking away energy from the system. Okay? Yep, so that's what we have so far. Okay, let's look at how we can also use graphing to solve this. Alright. Basically, I know that you guys haven't learned about integration yet because you guys starting with vectors in maths, right? But if you have taken A maths before in secondary school, it's not too hard. Okay, essentially what we are doing is that when we have a force displacement graph, right, the work done is the area under the graph. Okay, don't worry too much about the integration. It will make more sense to you as you go through your H2 math syllabus. Okay, so for physics, right, there's no need to use integration to solve this kind of questions. Most of graphs, if you are asked to calculate, you are given very decent values or straight line graph, and it's definitely easier to calculate. If we give you a curve like this, right, what you're usually expected to do is to estimate the area under the curve. So you could basically slice this up into neater shapes. Like for example, you can slice into one trapezium and one big rectangle and one more trapezium here. That will give you a good estimate of the area, which is the work done by your force. Okay, let's look at example 3 now. Okay, I have a force Fx that's acting on a object erased with displacement x as shown by the graph. Calculate the net work done by the force as the object moves from x equals to 0 meters to x equals to 6 meters. Okay, this force here, this is not a constant force, it varies with the displacement. Alright, so in this case, we have to find the area under the graph. Alright, so you just need to be careful that there are two types of area here. There is the positive area, which is the area that's above my x-axis, and there's also the negative area. So if this section here where my mouse is moving over, this part has to be added positively, and this part here, this small triangle here, has to be added negatively. Alright, so I have 5 times 2, which is this big rectangle here, then half times 2 times 5. Okay, 2 comes from here, this is 4 minus 2 times 5 times half, because this is a triangle. And then do the same for the other side, half times 2 times negative 5. So you sum this up, you get a total of 10 joules. Alright. Okay. So again, because like I said just now, work done is negative from 4 to 6 meters as my force is in the opposite direction. Remember this displacement at the start, it was a positive force compared to not positive force. The force is in the same direction as your displacement because displacement is positive, and then this 5 is also positive. But once it crosses here, it will start to become a negative force compared to your displacement. Alright, so it's the opposite direction. Okay, next let's move on to work done by gas. Alright, so work done by gas, right? Okay, gas has pressure, so gas will do work as well. Alright, so how do we do it on the gas? Okay, work is done on the gas by external forces when its volume is reduced. Okay, when you compress a gas, positive work is done on the gas. Alright, but when you allow the gas to expand, right, positive work is done by the gas. Okay, because the gas, remember, the pressure is pushing outwards, and then therefore if it expands, right, it's moving the direction of the force. Alright, so if I have no changes in volume for my gas, no work is done. Okay, so these are the basic concepts for this work done part. Okay, but for now, right, we will just basically talk about the formula. You don't really have to worry too much about how to derive the formula for now. For that, we'll talk more about it when we do thermal. Okay, so how do we calculate work done by a gas, right? So remember, work done by a force is the the product of the force with the displacement in the direction. So that's force times displacement x. Okay, so if I have a cylinder of gas, this looks this way. So I allow the force to push the gas outwards, to push this piston outwards, okay, by this delta x. Alright, so if I have this, okay, so I have this gas with an internal pressure of P(ext), okay, then assuming this cross-sectional area is A, I allow my gas to move outwards. Okay, so if I want, because I know this is A, I know that this is delta x, I can find the change in volume here. Alright, so if I assume this, then I know that force is equal to pressure times cross-sectional area, and then I sub it into this formula on top here. So this will become work equals to PA, pressure times cross-sectional area, multiplied by change in x. Okay, and if I shift the A inwards, okay, then this becomes P delta V. Alright, so yeah, basically don't have to be too worried about whether you should sub in negative number or positive number. It's easier to just recognize whether the gas is expanding or contracting, then decide whether it's work done by or whether it's positive work done by or negative work done by, or positive work done on, negative work done on. But let's look at one example and then it should be clearer to you. Okay, so anyway, this is the summary. So if my gas is being compressed, positive work is done on the gas, positive work is done by the gas. If it's expansion, negative work is done on the gas, and then positive work is done by the gas. If there's constant volume, there's no work done on or work done by. Okay, let's look at one example here. Example 4. A gas expands at constant pressure of 1.5 times 10 power 4 Pascal, and its volume changes from 0.8 times 10 power negative 4 meter cube to 1.2 times 10 power negative 4 meter cube. Calculate the work done by the gas. Okay, so look at this first diagram here. I'm allowing the gas to expand. Okay, so the displacement of the piston is in the same direction as my force. Right, so in this case, this will be, because I'm looking for work done by the gas, this is positive work done by the gas. Alright, so I think the math is simple. It's just basically pressure times change in volume. Okay, for this one, if they ask you what is the work done on the gas, it will be the same number but negative. Alright, next we are asked to do B, work done by the gas if the gas was compressed by the same volume instead. So now, remember the gas pressure is always pushing outwards on the piston, okay, but external pressure is pushing it in. And in this case now, my piston is moving inwards, which is the opposite direction of my the gas pressure. Okay, the force due to the gas pressure. So if this is the case, I would make sure that this is now 0.8 times 10 negative 4 minus 1.2 times 10 negative 4. Okay, it's the other way around. Final minus initial. Okay, and I'll get negative 0.60 joules. Okay, so make sure you have the negative value there. Alright. Okay, next let's move on to kinetic energy. This is something that you've learned before, but let's just formally define it one more time. Kinetic energy is a type of energy which a body possesses by virtue of its motion. Okay, note now we are talking about energy, right? We are not, okay, work done and energy both have the same values, right? But energy is possessed by the body itself. When you do work on the body, you are either taking away energy from the body or you're adding energy into the body. Okay, so right now let's look at energy, kinetic energy to be clear. Okay, so we know this to be half mv squared, but for A levels, right, you need to know how to derive it as well. Okay, how do we derive it? Okay, so let's assume that we have a mass m, and then I apply a force on it. But before I apply the force on it, it has a current velocity of u. Alright, so once I apply this force, I expect this force to be able to accelerate this mass. Okay, and it will travel by a distance of s, and then it will gain velocity to get velocity v. Okay, so let's look at what we can do to derive our half mv squared here. Okay, first thing first, okay, by Newton's second law, we know F equals to ma. So a force F produces an acceleration of A on mass m. So basically A is equals to F over m. Alright, next, work done by force F on mass m, right? Work done is what we derived earlier. Work done equals to force times displacement. But now we open up our force, it will become ma times s. And once we do that, we can rearrange it a little bit to get m times as. So it's just a shifting of the brackets. Okay, and if you remember your kinematics equation, I have v squared equals to u squared plus 2as. Okay, what I'll do is that I'll rearrange this equation to make as the subject. So I get as equals to half times v squared minus u squared. Take this as value and throw into this equation here. So sub into this equation here. So I have work done equals to m times half times v squared minus u squared. Alright, so we are getting very, very close to the actual equation now. So remember, work done will tell you also the change in energy as well. Alright. Okay, so if my u is 0, that means my initial velocity is 0, right? My work done equation will simplify to half mv squared. So if I make the assumption that all the work done by this force is converted into kinetic energy, right? Therefore, the kinetic energy is equals to half mv squared. This is the formula that you are very familiar with. Alright, but right now you need to know how to derive this formula. Okay? Okay, so next let's move on. Okay, we talk about work energy theorem. Okay, work energy theorem is a relatively new concept to you, but once we explain it, I think it'll be clearer. Alright? So what this is saying is that, okay, you don't really need to know how to derive this you don't need to know how to write out this definition. But what you need to understand is that when I have a rigid body, okay, what is a rigid body, right? A rigid body is a body where the shape cannot change. Okay, it's not flexible at all. It's rigid. It's hard. Okay, so the work done on a rigid body by the resultant force is always equal to the change in Ke of the body. All right. So if I work out all the forces that's acting on the body, I find the resultant force. I multiply it by the distance moved in the force, I will get the work done. Okay, and this is equal to the change in kinetic energy. Alright, so basically, right, it also means that if I take the work done by each of the force on the body and then sum them up algebraically, right, I also get the change in Ke of the body. So you go back to, let's say, example 1, where you have like 3 to 4 forces acting on the same body, right? I could of course work out the resultant force and then find the work done through displacement, or I can find the work done by each of the force, then I sum them up, and that should give me my change in kinetic energy. Alright, so let's see how this is applied in reality. Okay, example 6 here, I have an 80 kg box that's sliding down a 30-degree slope. Okay, throughout the motion, the box experiences a constant frictional force of 110 newtons, which is definitely upwards here because the box is sliding down. Okay, given that the speed of the box is 1.8 meters per second at the top of the slope, calculate the speed of the box at the point after it has slid 15 meters down the slope using work energy theorem. Okay, so what this question is doing is that it is using what the method is doing here is using all the forces that are acting on it. Okay, finding the net force first, then applying the work done directly. So in this case here, there are two forces that are concerning. Remember, this work done, this weight can be split into the parallel and perpendicular component, and only the parallel component will affect it. And the parallel component is given by W sine 30. Okay, there's of course a normal force on the box due to the slope, but because it's acting perpendicular to the slope, right, we don't really care about it. Okay, then minus 110, which is the force that's acting in the opposite direction as your weight. Okay, so basically if you work out the net force, this is 282.4 newtons. Right, then after that you just apply work energy theorem, which is the change in kinetic energy is the work done by the resultant force. Okay, so you take this final EK. So if you write this out, this work done here is 282.4 times 15, and then you write out the change in kinetic energy. 1.8 is the initial velocity, so half 80 v squared minus half 80 1.8 squared. Do the math, you get final v of 10.4 meters per second. Okay, personally, I don't really like this method because I think this step is not so intuitive to get. Okay, let me show you what we can do if we do it using another approach. Okay, first we find the work done by each force here. Alright, so we know that this has slid down by 15 meters. I also can find the height that it has slid down by. So this is 15 cosine 30. 15 sine 30. Okay, so let's just check this. Okay, work done by the weight. So it's weight times vertical displacement. Weight is acting downwards. I just need to find the work done by the displacement of the box in this direction. which is 15 sine 30 degrees. Okay, so I get 5886 joules. Okay, next I'll find the work done by frictional force. Frictional force is acting up the slope, movement is down the slope, so 110 times negative 15, negative 1650 joules. Okay, I didn't write in the work done by normal reaction force, but you can just imagine because it's at a right angle, work done is 0. Alright, so I have these two work done by these two forces. So what I need to do now is just to add them up in terms of algebra. So just consider the sign when you add them up. So you add these two up, you get 5886 plus negative 1650. I get 4236 joules. Then now I apply work energy theorem. Okay, so total work done is equals to change in kinetic energy. So total work done is 4236 joules. Then do the half m v squared minus u squared, sub in the value for u, and then you will continue to get v equals to 10.4 meters per second, which is the same answer as the previous page. Okay, so for me, I think this method is cleaner because it's easier to work out the work done by the forces first, each of the force, and then sum them up together. Okay, next we move on to energy possessed by a mass by virtue of its position in the gravitational field. That's your GPE. Okay, so again, that's something you have learned before, mgh, right? Okay, but we're going to again learn how to derive it, and we're going to write a more general version of it as well. Alright, so let's look at the setup again. Right, so let's click through. So again, I have a mass m, and of course mass has a weight acting downwards, and now I exert an upward force on it. Okay, the current velocity is v. Okay, then now let me start this experiment. So if I let it run, the box will move upwards. Okay, but at the end of it, the velocity is still v. Okay, the force is still the same, the weight is still the same. I have changed this by a distance of h. Okay, h here. So it has gained this amount of height. Okay, let's look at the steps involved. First thing first, since the mass was lifted at constant velocity, there's no change in velocity, acceleration is equal to 0. If acceleration is 0, that means the net force is also 0 as well. That means F here is the same as W. So F is equal to mg. Alright, next thing, since the velocity has no change, is constant, there's no change in kinetic energy as well. So whatever work done on the mass is used to gain GPE. It is not used to gain KE because there's no change in your KE value. Okay, so my change in potential energy is equal to the work done by the force on m. Okay, so in this case here, remember work done is just force times this displacement. So this is mgh. Okay, so my change in potential energy, change in GP is equal to mgh. Okay, so what we can do is that when we take GP to be 0 at reference height, right, then I can say EP, okay, my total potential energy is equals to total change in potential energy. Okay, what this is saying is that if I set this height here, if I set the GP here to be 0, okay, and from here to here, the top, I gain mgh of GP. Okay, so my delta GPE is equals to mgh. Okay, but if my original GP is 0, that means my GP at the point is mgh. Okay, but h has to always be given to a certain point of reference. Okay, this is similar concept to your displacement. When you talk about this displacement, you're always referring to a reference point. So you're measuring always from that reference point. Okay, next slide. Okay, we're going to move on to elastic potential energy. There'll be questions involving EPE and GPE later on as well. Okay, so EP, Hooke's law you might have learned before in secondary school, or you have seen some concepts of it. Okay, so energy stored in the mass that is based on the degree of elastic deformation, which is the amount of compression or extension. So if you take elastic object, let's say you have a rubber band. I have one. No, I don't have one here. Okay, if you stretch the rubber band, it will extend. So this is considered as deformation. If you have a piece of sponge, you compress it. That is also considered as compression. That is a deformation. Okay, so you can feel that when you compress a spring or you stretch a rubber band, the object will want to restore itself to its original position, original size. The ability to do that is because it is storing elastic potential energy. Okay, it has a potential to do work, right? Okay, so let's go on. Okay, how to derive EP? Again, there's some math involved. Okay, consider a spring that has been stretched or compressed by an applied force F. Okay, so remember I now have a graph of this force and extension. Extension, remember, is the difference between the stretch or compressed length minus away the original length. So if you are not stretching anything, your extension is 0. Okay, so if you stretch it, so this is the stretching. Remember, because Hooke's law is still obeyed within the limit of proportionality, this is a constant gradient cutting through 0. Alright, so again, area under the graph, force times the displacement graph, right? I will do some integration. Again, don't worry too much about integration. Effectively, when you want to find the work done by a force, you are looking for the area under the graph. So in this case, if I'm talking about Hooke's law range, right, it will be a right angle triangle. You can just do half fx here. So if I want to find this blue color area, I take the force here, multiply by the extension here, then divide by 2. Okay, so that's the area under the graph. Okay, and yeah, so even if my force extension graph is non-linear, the elastic potential energy is still the area under the graph. So I can draw this as a curved line, that's fine as well. The work done by the EP stored is equals to the area under the graph. Okay, so that also brings it to another point, right? If I want to do work on this, if I want to extend this rubber band or something by this length of x, right, I need to do this amount of work on the rubber band. I need to give it this amount of energy. So if I want to stretch this rubber band, I have to use my hand to pull. I'm using my own energy, and I'm transferring the energy into the rubber band as elastic potential energy. Alright. Okay, let's look at some questions, I think. Okay, so I have a spring obeying Hooke's law, has an unstretched length of 50 millimeters and a spring constant of 400 Newton per meter. Determine the tension in the spring when its overall length is 70 millimeters. Right now, in case you don't know where we are, we're at example 7. Okay, so let's determine the tension in the spring. Okay, so let's do this. To find tension in spring, right, is equals to the force applied to the spring. Okay, to find this force, I'll just apply F equals to kx. Right, so K is 400 Newton per meter. X is given in terms of mm, so you need to convert them. 70 minus 50 times 10 power negative 3. So I get a total of 8.0 newtons of tension. Okay. Next, you're asked to calculate the change in EPE when the spring length is changed from 70 mm to 60 mm. Alright. So okay, you might think that I will just use because length has changed by 10 mm, so I just use half kx squared, x will be 10 mm. You can't do that because you have to always take the current, okay, you have to take the initial total amount EPE minus the new EPE. So to find, you need to do half kx squared for each of them. Okay, so to do this, delta EP equals to half kx f squared final extension minus half kx I squared, where I is initial extension. So substituting the value 400, then 60 times 10 negative 3, 70 times 10 negative 3, I get negative 0.26 joule. It's negative because in this case my spring has become slightly less stretched, so it's given up some of its elastic potential energy. Okay. Alright, so this is example 7. Okay, moving on, let's look at the different types of potential energy first. Okay, so if we talk about elastic potential energy, you should be able to explain this at least right now in brief. Okay, so basically when you do elastic potential energy, right, you are moving the molecules or atoms further apart. You are changing their short range interatomic attractive or repulsive forces. So GPE is energy of the mass by virtue of its position in its G field other masses. Okay, so usually we talk about G field of Earth. So in this case, energy of a mass by virtue of its position in Earth's gravitational field. Okay, electric potential energy you'll learn next year. Okay, energy possessed by electric charge when it's within the electric field of another charge. Okay, so don't worry too much about, especially the last one right now. You should be concerned about the first two for now. Okay, let's look at example 8. Okay, so this is basically GPE to KE. EPE to KE. So I have 2 kg mass pressed against a spring by external force F as shown. Spring and block are not secured to each other, so basically they will separate out. Spring is compressed by 10 cm from its unstretched length. The block is then released and accelerated until it leaves the spring at 0. So basically this spring is pushing the block forward. Okay, find the work done in compressing the spring. Alright, so we know the spring constant, we know the compression, so we can just do it very quickly. Half kx squared. So half times 500 times 0.100 squared, 2.5 joules. So right now the spring has stored 2.5 joules of energy. When you release this energy, it is converted to kinetic energy of the block. Okay, so right now the block is stationary. All the EP is used to gain to help the block gain kinetic energy. So basically, I half mv square minus half mu square equals to 2.5 joules. Change in Ke is equals to change in EPE. Okay, since I set my u to be 0, initial speed is 0, my velocity, if you do the math, is 1.6 meters per second. Alright. Okay, next, let's look at example 9. Example 9 is a bit more challenging. Okay, you have a spring of length 18 cm and spring constant 250 Newton meter is placed vertically on the ground as shown. A 500 gram block of height 3 cm is released at a height of 6 cm above the spring. Determine the maximum compression of the spring. So what's going to happen is that this block is going to fall by 6 cm before it hits the spring, and then it will compress by a certain amount as well of x. Okay, so if you think about it, right, the loss in GP is 6 plus x, the loss in height is 6 plus x. Okay, but before the block hits the spring, right, it is not getting EP first. It will lose GPE and gain KE. So there are some stages that we need to look at. Okay, so let's just click through first. Okay, at the start, right, you only have GP because at the start, at this top here is not moving. You only have gravitational potential energy. But once you start to drop it, before it hits the spring, you will have GP and KE. You will have lost some of the GPE, but you're gaining KE in return. Okay, but once it hits the spring, it is still moving while compressing the spring. So once the spring is compressed, you have less GP than beforehand, you have a little bit less KE than beforehand, and then you also have, you're getting some EP as well. Eventually what happens when the spring comes to a stop, you will only have EP. So you'll note the colors here. Okay, I don't really need to care about what's happening in the middle here because I just want to know the maximum compression of the spring. This is when the spring has stopped. Okay, so I just need to compare this GP and K and EP at the end. Okay, so if I write this, that means all the GP that's lost is gained as elastic potential energy of the spring. Okay, because the box is no longer holding any kinetic energy. Okay, so let's see how I can write this out. Loss in GP equals the loss gain in EPE. So the loss in GP is equals to mg times 6 cm plus the x over here. Okay, and gain in EPE, the spring is compressed by x squared. So okay, if you do the math, okay, just expand it out properly and then just be careful in your steps. You get two values of x, 0.07196 and negative 0.0237. We will reject the negative answer because we are taking downwards as positive here, and then we'll get 0.072 meters instead. Okay. Yep. So yep, this is how we can do this question. Okay, so just be careful in the math part. Okay, let's move on to the next part. We are looking at conservation of energy now. Okay, so this is something that again you have learned before, but I'm just going to make it more contextualized for the A levels. Okay, total energy of an isolated system is constant. Energy cannot be created or destroyed, but may be transformed from one form to another. So what we're saying is that if we have a system that is isolated, that means I'm taking away all other things like frictional force, drag force, etc., right? So there's no way energy can come in or go out of the system, right? You cannot create or destroy energy. That means the total energy within the system will stay the same, but it could be stored in different forms. Okay, so for example, if you have a closed system, when an object is falling, okay, so it's converting GP to KE, so that's fine as well. Alright. Okay, let's look at some of the examples we have over here. So let's write this out a little bit clearly. Okay, so this is total initial mechanical energy. Okay, but if I supply energy in the system, alright, I can still but this would be equal to the total final mechanical energy plus the energy lost to dissipative forces. So if I expand my system to allow energy to come in, to energy to be supplied in, and so energy be lost to, let's say, like friction or drag force, right? The total system is still balanced. Okay, so I will never gain or lose energy in the system. All right. So next, so again, write in the equation, K initial plus P initial plus energy supply is equals to KE final plus PE final plus energy lost due to dissipative forces. Alright, so this so this energy supplied could be work done by another force as well. Okay, next you have conservation of mechanical energy. Okay, so mechanical energy is defined as kinetic energy plus potential energy. Okay, so if you go on to this, total initial mechanical energy is equals to total final mechanical energy. So this is a case where I don't allow for any energy to be supplied into the system. I also don't allow for energy to be lost out of the system as well. Right? Again, write the equation KE initial plus P initial is equals to KE final plus PE final. Right? Okay, next, then you have your loss in KE is equals to gain in PE. So again, when we talk about conservation of mechanical energy, right, we are just rearranging this equation here. If I shift KE final to this side and P initial to the other side, right, you can see that essentially what I'm doing is that I have loss in KE equals to gain in PE. And the converse will also apply. Gain in KE is equals to loss in PE. So for example, if your object is falling down, you are gaining PE but losing potential energy. Right? Okay, let's go on with this. Okay, and one more thing we can do, if we add up the change in kinetic energy plus the change in potential energy, this is the algebraic sum, remember, that it will be equals to 0. Okay, because the net change of energy in the system is 0. Okay, whatever gains you have for one type of energy, you'll be offset by losses of energy in the losses of the other type of energy. Okay, let's try one of the questions. Example 11. A block of mass 5 kg is released from rest at the top of an incline and pulled horizontally by constant force F. So this force F is pulling this way. The box experiences a constant retarding force of 3.0 newtons due to friction. So friction is acting upwards there, up along the slope. Okay, so first thing first, draw a free body diagram on the block, then calculate the speed of the block at the bottom of the incline. So free body diagram, I'm just going to show you very quickly. Okay, it will look like this. Okay, so normal reaction force pointing perpendicular up on the slope. The weight will be downwards, and this horizontal force of 7 newtons will be pulling this way. Angle between here is 30 degrees, and then this force is 3.0 newtons. Okay, so calculate the speed of the block at the bottom of the incline. Okay, so we have the free body diagram there. So let's look at how we can calculate speed of the block. Before we show the answers, right, I'm just going to quickly run through which of the forces are doing work. Okay, so let's quickly rule out normal reaction force. Normal reaction force is not doing work at all because it's perpendicular to the displacement of the box. So that's fine, we can take it out. Okay, the frictional force is doing work because it's opposite direction from the displacement. So that's okay. We will just need to calculate with the negative value. Right? Weight also is down vertically downwards, but it also has a component that could be extracted that's pointing in the direction of the slope. Okay, same for the 7 newtons force. Okay, I also could extract the component that's parallel to the slope. Right, so let's see how the math goes, right? Okay, so let the bottom of the incline be reference point for GP. So what I'm doing here is that I'm setting the load here, this point here, to be GP 0. Remember we talked about GP, we must always start with a reference point where your GP is 0 value. Okay, next let's look at the math. Okay, so we are using conservation of energy. Initial KE plus initial GP plus energy supplied into the system is equals to KE final plus GP final plus energy lost due to dissipative forces. Okay, so let's do the substitution. Initial KE is 0 because at the top it's not moving. Okay, GP initial 5 times 9.81 times 4 times sine 30. Alright, this height here is 2 meters. I should have just written 2 meters, but I went to solve it, but it's actually just 2 meters here. So 5 times 9.81 times 2. Okay, then the GP, then this 7 times 4 times cosine 30 is from this force here. This 7 Newton force would have caused this block to move forward by 4 cosine 30. Okay, and then this is equal to KE final, which is what we want to find. GP final at the bottom is 0, and then energy lost due to dissipative forces. Okay, so dissipative forces here, this is 3 newtons upwards, 3 newtons up the slope, but displacement 4 meters down the slope. You note that here I didn't put in the negative sign because this one is already talking about energy loss. Okay, so loss itself is already negative. We are just substituting in the modulus of the number. Okay, and do the math for this one to find KE final. You get V equals to 6.6 meters per second. Alright, so just be careful with the substitution. Yeah. So example 11. Okay, next let's move on to power and efficiency. Okay, power you have learned before, I believe. Power is defined as the rate of work done or energy transfer. Okay, so basically, if you do it properly, right, you should be writing delta W over delta T for work done over a period of time. Okay, but if you have a constant rate of work done, you can basically take P equals to W over T. That's fine as well. So the unit is just watt, W-A-T-T, or joule per second, joules, J-S -1, right? Okay, so this is something new. So we want to talk about power, force, and velocity together. So suppose you have a constant force F acting on the body, and the body displaces by S in the direction of the force in time t. Okay, so if you do the math, right, remember power is rate of change of work done, right? Rate of change of work done, right? Yeah. So then if I sub this in W in, W will be equals to Fs. Okay, Fs and this T. If I take out the F, I get, because it's a constant force, so there's nothing to differentiate from there. So it's ds over dt. This is rate of change of displacement over time, which is velocity here. Alright, so you have this useful formula where you have P equals to Fv. Okay, in this case here, my P is my instantaneous power, F is instantaneous force, and V is instantaneous velocity. Alright, so let's see how we can use this formula. Okay, example 14 now. A vehicle is traveling at a constant speed of 32 meters per second on the expressway. Okay, the direction of the drag force acting on it is 870 newtons. Determine the power delivered by the vehicle's engine while traveling at this speed. So let's quickly draw a simple diagram. I have a car there, and this car is traveling at a constant speed of 32 meters per second. Okay, next, it will have a driving force F and a drag force D that's in the opposite direction. Okay, since the velocity is constant, right, my net force is 0. Okay, so the driving force will therefore be equal to the drag force, which is equals to 870 newtons. So to find the power of the engine, I'll just take I'll just take the driving force F multiplied by velocity. So 870 times the velocity of 32 meters per second. So I get 27,800 watts. Okay, so that's how you usually apply for your P equals Fv. Okay, next there is another new concept that you will learn. It's called efficiency. So when we talk about machines, right, we know that machines are not perfect. When the machine uses a certain amount of energy, not the same amount of work is being done. Okay, so some of it is used within the machine to overcome friction, overcome drag force, and so forth. Sound is produced, etc. Right, so all these things causes loss of energy. So you don't expect machines to be 100% efficient. So with that in mind, we can work out what's the efficiency of the machine. So how do we do this? We look at the energy that's given to the machine in terms of the fuel or whatever work we do. Okay, then how much useful energy we get from it. Okay, so we take useful energy output divided by energy input, then multiply by 100%. We get a percentage. Okay, another way is to look at the power instead. So again, useful power output divided by power input, then multiply by 100%. Okay, so note that energy input here, right, we are talking about the sum of the useful energy output plus the wasted energy output, not wasted, okay? So these two together should give you back your energy input. Same for power as well. So power input equals useful power output plus wasted power output, okay? Okay, so example 15 here, I believe this is my last slide. Okay, so I have an electric motor that hauls a heavy metal beam of mass 400 kg up a mine shaft at a steady speed of 0.85 meters per second. Calculate the useful power of the motor, electrical power required by motor if its efficiency is 80%, work done by the motor on the beam in 20 seconds. So let's do the math very quickly. Okay, so useful power, okay, this is the actual work that's done. So we don't look at what the machine we look at what is actually being done. So in this case, the shaft, the metal beam is moving up 400 kg, and then we can do 400 times 9.81 times 0.85. Why times 0.85 here? Okay, because I'm taking mgh over t, right? M and g are constants. H and t here, right? What I can do is that h and t is essentially average velocity. Since velocity here is constant, I can just use 0.85. So 400 times 9.81 times 0.85. So I get 3335 watts. Okay, Yep. Another way of looking at this is to use P equals FV. So F, the force required to lift this beam at constant velocity will be equals to this weight. So 400 times 9.81 times V, which is 0.85. Okay, electrical power required by motor if its efficiency is 80%. So 3400 watts here is the useful power output, and this represents 80% of the total input. Okay, so let's see how much the motor needs, right? So efficiency again is eta. Eta is P useful over P input. Okay, so if I sub in the value, this eta is equal to 80, so I have 3335 over P input times 100%. If I do the calculations correctly, I'll get 4169, which will round off to 4200 watts. So I have to put in 4200 watts of power to get 3400 watts of power back, useful power output. Okay, next, work done by the electric motor on the beam in 20 seconds. Here we are referring to the useful work done. Okay, we can say that the motor has done 4200 joules of work per second, but not all of it is useful. Only 3335 of it is useful. So 3335 multiplied by 20, I'll get 67,000 joules. Okay, this is the last slide. So you can make sure you complete all the questions as well inside this lecture. Also, think about what you have learned, what is new to you so far after going through this set of slides. Okay, so there's the interactive thinking tool on the last page. Make sure that you complete that as well. Just pen in your thoughts so that your classmates also can see what you're thinking of. You also can see what your classmates are thinking of. Okay, so that's it for this topic. We'll move on to the next topic next week, or rather the week after your common test. Good luck for common test too.